Hi, welcome to video 8.5D, part 1, more logistic growth.
Equation where the rate of change of a quantity y with respect to time is directly proportional to equals k times the quantity and the difference between a maximum capacity constant and that quantity. All right, I actually do want to look at the book so you can see what I'm talking about. This is in the book on page 562. They actually don't talk about logistic growth within the section. It's one of the questions. So here's what they say. In Chapter 6, the exponential growth equation was derived from the assumption that the rate of growth was proportional to the existing quantity. In practice, there often exists some upper limit at L past which growth cannot occur. So, for example, if you have a school and there's 1,000 people there, you can't have 2,000 of those people getting the flu. The maximum number of people at that school who can get the flu would be that upper limit. In such cases, you assume the rate of growth to be proportional not only to the existing quantity, but also to the difference between the existing quantity y and the upper limit L, which is a constant. So it becomes dy dt equals k times y times L minus y. In integral form, if you separate the variables, so you bring the t's to the left and the y's, t's to the right, y's to the left, and leave the k where it is because it's a constant, you'll be integrating this. And of course, the reason it's in this section is to integrate this, you have to use partial fractions. So, going back to our notes, and you can see the next page, and this is just a review actually of what I did at the end of the last video. On the next page, I'll show you how this becomes this. Unless they ask you to show the work in the free response on the AP to actually solve the differential equation, you can go directly from here to here. So it's y equals a over 1 plus b times e to the negative akt. The a is that famous maximum quantity possible. So if there was 1,000 people at our school, that would mean the maximum number of people that can get a disease or hear a rumor would be 1,000. So that's a constant. The y is how many people have gotten the flu or heard the rumor. So that's the quantity that's varying. It's varying with respect to time. More time goes by, more people get the flu. More time goes by, more people hear the rumor. Now, the b and the k are constants. The e, of course, is the constant e. So the way this graph will look, if I replace t by 0, this whole exponent becomes 0. E to the 0 is 1. I'm left with a over 1 plus b. So that's where I'm starting. That's kind of patient 0. The first person who gets the flu, the first person who hears the rumor. And then what happens is more and more people will get the flu. It's growing at a very fast rate. But then eventually, when half the people in the school have the flu, they can no longer get the flu. So now there's fewer and it's still spreading the disease, but there's fewer and fewer people that are apt to get the flu now because the others already had the flu. Okay, and of course there's our horizontal asymptote y equals our famous a, which is our maximum quantity. Okay, so the idea is to come up with an equation in the two variables, y, which is how many people have the flu, how many people have heard the rumor, and t, which is the passage of time. They'll give you the A, which is the maximum population. It's going to be up to you to find the B and the K. So, here's the actual solving of it. Again, I did this the other day. I would make this a bonus question. I've seen it once as a free response question where they actually asked you to solve it. And it wasn't even logistic growth, it was logistic decay, just to make it mean. Anyways, so what we're going to do is we're going to bring the t's to the right side and all the y's to the left side. We'll leave the k there because it's a constant. Integrate both sides. This has to be done by partial fractions. You have two fractions, one with the denominator of y, one with the denominator of a minus y. Multiply both sides by the LCD. Let y equal a, let y equal 0, blah, blah, blah. You get this. And then I had walked you all through this. You can certainly pause at this point in time. Careful here, if you let u equal your denominator, your du is negative 1 dy, so you'd have to introduce that negative and counteract. 1 over a is just a constant. Over here you have kt plus c1. They pull out the 1 over a, then they pull out a negative, which is weird. Then they multiply both sides by negative a, and then of course the really tricky, then they rewrite it in exponential form, but this is the tricky step where they break this up into e to this power times e to that power. Anyways, and then etc., 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 you can certainly look at all this. So you can be very happy to know that I will let you go directly from here to there. If it's multiple choice, no one will know how you got from step A to step Z. And on the AP, as I said, even in the free response, they have to specifically ask you to solve a differential equation. Now, I do want you to notice that the book doesn't talk about logistic decay, but the only difference would be instead of a minus y, it would be y minus a. So if we look at number 64 on page 62, they give you a slope field. You'll notice this is a logistic growth equation because it's dy dt equals k, which happens to be 1 here, times y times parentheses capital A minus y, and your capital A happens to be 3. Draw a possible solution to the differential equation if y of 0 equals 5 and another if y of 0 equals a half. So here's y of 0 equals a half right here, and you can see it has that shape to it. Y of 0 equals 5, it'll come down in this way right here. So, not a very exciting question. The second question is, let me actually go back to the actual question. Okay, so that was part A, and here's part B. So let me actually put these questions right here for you. Ooh, that's not going to work. Take it back. This will work. I don't know why it has all those little lines in it. Oh, that's not looking good, is it? Let's see what happened. Wrong video. Okay, I don't know why those lines are there, but whatever. Where y of 0 is greater than c3, what is the sign of the slope of the solution? So, going back to our notes. Oh, I keep picking on the wrong one. Okay, so let me just cut this whole thing and bring it back over here. And let me make this a whole lot smaller so that you can see it over here. Okay, so part B, where y of 0 is greater than 3. So y of 0 is bigger than 3 means at the top half, above this line right here. What is the sign of the slope of the solution? Well, as you can see in each case, these are decreasing, these curves, so the slope would be negative. C, for y is bigger than 0, find the limit as t goes to infinity of y of t. If you let t go to infinity, whether you're approaching it from the bottom or from the top, you're approaching this height of 3. So as t approaches infinity, y of t is equal to 3. Evaluate the two given intervals and solve for y as a function of t, where y0 is the initial quantity. So that's basically me going through the procedure here. dy dt equals k times y times a minus y becomes that equation that we know. So I'm just redoing it. They're using L and I use A, so that's really the only difference. E, use the result of part D, find and graph the solutions in part A. So in part D, we ended up with, we started with this, dy dt equals k times y times a minus y. The k was 1, the y was 3, so this implies the k is 1 and L is 3. Number for y of 0 equals 5. I mean, you can read through all this. This is not really super important. They're going to take the derivative, so they're going to have a product rule, and that's where it says show that the rate of growth is maximum at the point of inflection. So for the rate of growth to be a maximum, that means the derivative of the rate of growth would have to be equal to 0. So the rate of growth is already the derivative. So the derivative of that would be the second derivative. You'd have to set it equal to 0. So you go from the first derivative to the second derivative with a quotient rule, and you'd set it equal to 0, and that'll happen when y is equal to L over 2.